Hello students, welcome to my OOAD through UML class 3. Today we are going to discuss about classes and objects. In these classes and objects, the first topic is nature of an object. The ability to recognize physical objects is a skill that human learns at early age. A brightly colored ball will attract an infant's attention, but typically, if you hide the ball, the child will not try to look for it. When the object leaves her field of vision, as far as she can determine, it ceases to exist. It is not until near the age of 1 that a child normally develops what is called the object concept, a skill that is critical importance to future cognitive development. Show a ball to 1 year old and then hide it, and she will usually search for it, even though it is not visible. From the perspective of human cognition, an object is any of the following: a tangible or visible thing, something that may be apprehended intellectually, something toward which thought or action is directed. An object has state, behavior, and identity. The structure and behavior of similar objects are defined in their common class. The terms instance and object are interchangeable. State semantics. Consider a vending machine that dispenses soft drinks. The usual behavior of such objects is that when one puts coin in a slot and pushes a button to make a selection, a drink emerges from the machine. What happens if a user first makes a selection and then puts in the slot? Most vending machines just sit and do nothing because the user has violated the basic assumptions of their operations. Stated another way, the vending machine was playing a role that the user ignored. Similarly, suppose that the user ignores the warning light that says correct change only and puts in extra money. Most machines are used raw style. They will happily swallow the excess coins. The state of an object encompasses all the properties of to be object plus to be current values of each of these properties. Behavior. The meaning of behavior is no object exists in isolation, rather, objects are acted upon and themselves act upon other objects. Thus, we may say that behavior is how an object acts and reacts in terms of its state changes and message passing. In other words, the behavior of an object represents its outwardly visible and testable activity. Identity. Semantics of identity. Identity is the property of an object which distinguishes it from all other objects. They go on to note that most programming database languages use variable names to distinguish temporary objects, mixing addressability and identity. Most database systems use identifiers keys to distinguish persistent objects, mixing data value and identity. The failure to recognize the difference between the names of an object and the objects itself is the source of many kinds of errors in the object oriented programming. Relationships among objects. The kinds of relationships. An object by itself intensely uninteresting. Objects contribute to the behavior of a system by collaborating with one another. As Ingalls suggests, instead of a bit grinding processor wrapping and plundering data structures, we have a universe of well behaved objects that courteously ask each other to carry out their various desires. For example, consider the object structure of an airplane, which has been defined as a collection of parts having inherent tendency to fall to earth and requiring constant effort and supervision to stave off that outcome. Only the collaborative effort of all the component objects of an airplane enable it to fly. The relationship between any two objects encompasses the assumption that each makes about the other, including what operation can be performed and what behavior results. We have found that two kinds of object hierarchies are of particular interest in object oriented analysis and design, namely links, aggregations. Links. The term link derives from James Ramba, who defines it as a physical or conceptual connection between objects. An object collaborates with other objects through its links to these objects. Stated another way, a link denotes the specific association through which one object applies the services of another object, or through which connection may navigate to another. A line between two objects icon represents the existence of a link between two and means that messages may pass along this path. Messages are shown as directed lines representing the direction of message, with a label naming the message itself. Here we see the object. A controller has links to two instances of display item, although both A and B probably have links to the view in which they are shown. We have to choose highlight only such link from A to A view. Only across these links may one object send messages to another. As participation in a link, an object may play one of these three roles. actor, an object that can operate upon other object, but it is never operated upon by other objects. In some contexts, the term active object and actor are interchangeable. Server, an object that never operates upon other objects. It is only operated upon by other objects. Agent, an object that can both operate upon other objects and be operated by other object. An agent is usually created to do some work on behalf of an actor, another agent. Aggregation. Semantics, whereas links denotes peer to peer or client to server relationships. Aggregation denotes a whole by part hierarchy, which the ability to navigate from the whole to its parts. In this sense, aggregation is a special kind of association. For example, the object ramp controller has a link to the object growing ramp as well as an attribute h whole class is heater. The object ramp controller is thus the whole and h is the one of its parts. In other words, h is a part of the state of the object ramp controller. Given the object ramp controller, it is possible to find its corresponding heater h. Given an object such as h, it is possible to navigate its enclosing object, as also called its container, if and only if this knowledge is a part of the state of h. Aggregation may or may not denote physical containment. For example, an airplane is composed of wings, engines, landing gear, and so on. This is a case of physical containment. On the other hand, the relationship between a shareholder and her shares is an aggregation relationship that does not require physical containment. The shareholder uniquely owns shares, but the shares are no means a physical part of the shareholder. Rather, this whole part relationship is more conceptual and therefore less direct than physical aggregation of the parts that of an airplane. A nature of class. The concept of a class and an object that are tightly interwoven, for we cannot talk about an object without regard for its class. However, there are important differences between these two terms. Whereas an object is a concrete entity that exists in time and space, a class represents only an abstraction, the essence of an object as it were. Thus, we may speak of the class mammal, which represents the characteristics of common to all mammals. To identify a particular mammal in this class, we must speak of this mammal or that mammal. A class is a set of objects that share a common structure and a common behavior. A single object is simply an instance of a class. Interface and implementation. Mayer and Snyder have both suggested that programming is largely a matter of contracting the various functions of a larger problems are decomposed into smaller problems by subcontracting them to different elements of the design. Nowhere is this idea more evident than in the design classes, whereas an individual object is a concrete entity that performs some role in the overall system. The class captures the structure and behavior common to all related objects. Thus, a class serves as a sort of binding contract between an abstraction and all of its clients. By capturing these decisions in the interface of a class, a strongly typed programming language can detect violations of this contract during compilation. We can further divide the interfaces of class into three parts: public, a declaration that is accessible to all clients; a protected, a declaration that is accessible only to the class itself, its subclasses, and its friends; a private, a declaration that is accessible only to the class itself and its friends. Class life cycle. We may come to understand the behavior of a simple class just by understanding the semantics of its distinct public operations in isolation. However, the behavior of more interesting class, such as moving an instance of the class or scheduling an instance of the class, involves the interaction of their various operations over the lifetime of each of their instances. Relationships among classes. Consider for a moment the similarities and differences among following classes of objects. Uh, as relationships among classes. Consider for a daisy is a kind of flower, a rose is a kind of flower, a red rose and yellow roses are both kinds of roses. A petal is a part of both kinds of flowers. Ladybugs eat certain pests such as aphids, which may be interesting certain kinds of flowers. Specifically, most object-oriented programming languages provides direct support for some combination of relationships: association, inheritance, aggregation using instantiation metaclass. Association. In an automated system for retail point of sale, two of our key abstractions include products and sales. We may show a simple association between these two classes. The class products denotes the product sold as a part of a sale, and the class sale denotes the transaction through which several products were last sold. By implication, this association suggests bidirectional navigation. Given an instance of product, we should be able to locate the object denoting its sale, and given an instance of sale, we should be able to locate all the products sold during transaction. Inheritance. After space probes are launched, they report back to the ground stations with information regarding the status of important subsystems such as electrical power and propulsion systems and different sensors such as radiation sensors, mass spectrometers, cameras, micrometeorite collision detectors, and so on. Collectively, this relayed information is called telemetry data. Telemetry data is commonly transmitted as a bit stream consisting of a header, which includes a timestamp and some keys identifying the kind of information that follows, plus several frames of processed data from the various subsystems and sensors. Because this appears to be a straightforward aggregation of different kinds of data, we must be tempted to define record type for each kind of telemetry data. For example, in C++, we may write single inheritance. Simply stated, inheritance is a relationship among classes wherein one class shares the structure or behavior defined in one or more multiple classes. We call the class from which another class inherits its superclass. In our example of telemetry data is a superclass of electrical data. Similarly, we call a class that inherits from one or more classes a subclass. Electrical data is a subclass of telemetry data. Inheritance therefore defines and is a hierarchy among the classes in which subclass inherits from one or more superclasses. This is, in fact, the litmus test of an inheritance given classes A and B. If A is not a kind of B, then A should not be a class of sub B. In this sense, electrical data is a specialized kind of more generalized class telemetry data. The ability of a language to support this kind of inheritance distinguishes among object oriented from object based programming languages. Multiple inheritance. With single inheritance, each subclass exactly one superclass. However, as Blisides and Linton points out, although single inheritance is very useful, it often forces the programmer to derive from one of two equally attractive classes. This limits the applicability of predefined classes, often making it necessary to duplicate code. For example, no way to derive a graphic that is both circle and a picture. One must derive from one or the other and re-implement the functionality of the class that was excluded. Multiple inheritance is supported directly by languages such as C++ and CLOS, and to a limited degree by Smalltalk. The need for multiple inheritance in object-oriented programming languages is still a topic of great debate. In our experience, we find multiple inheritance to be like a parachute. You do not always need to it, but when you do, you are really happy to have it on hand. Aggregation. Aggregation relationships among classes have a direct parallel to aggregation relationships among the objects corresponding to these classes. Our earlier example of the ramp controller and growing ramp objects illustrated a link between two objects which we represented via using relationship between their corresponding classes, temperature control and temperature ramp. Instantiation. Our earlier declaration of the class queues was not very satisfying because its abstraction was not type safe. We can vastly improve our abstraction by using languages such as ADA, C++, and EFIL that supports genericity. For example, we might write our earlier classes declaration using a parameterized class in C++. Meta class. We have said that every object is an instance of some class. What if we treat a class itself as the object that can be manipulated to do? We must ask, what is the classes of a class? The answer is simply a meta class. To state it another way, a meta class is a class whose instances are themselves classes. Usually, a Smalltalk and CLOs support the concept of a meta class directly, but C++ does not support the concept of meta class. Indeed, the idea of meta class takes the idea of the object model to its natural completion in pure object oriented programming languages. Interplay between the classes relation and the objects also, and the relationships between the classes and objects. Classes and objects are separate yet intimately related concepts. Specifically, every object is the instance of some class, and every class has 0 or more instances. For practically all applications, classes are static. Therefore, their existence, semantics, and relationships are fixed prior to the execution of a program. Similarly, the class of most objects is static, meaning that once an object is created, its class is fixed. In sharp contrast, however, objects are typically created and destroyed at a furious rate during lifetime of an application. For example, consider the classes and objects in the implementation of traffic control systems. Some of the more important abstraction includes planes, flight plans, runways, and airspaces. Some of the more important abstractions include planes, flight plans, runways, and airspaces. By their very definition, the meaning of these classes of objects are relatively static. They must be static. for otherwise one could not build an application that embodied knowledge of such common sense facts as that planes can take off, fly, and then land, and the two planes should not occupy the same space at the same time. Conversely, the instance of these classes are dynamic. At fairly slow rate, new runways are built and old ones are deactivated. Faster yet, new flight plans are filed and old ones are filed away. With great frequency, new planes enter a particular airspace and old one leaves. Role of classes and objects in analysis and design. During analysis and the early stages of design, the developer has two primary tasks: identify the classes and objects that form the vocabulary of the problem domain, invent the structure whereby sets of objects work together to provide the behaviors that satisfy the requirements of the problem. Collectively, we call such classes and objects the key abstractions of the problem, and we call these cooperative structures the mechanisms of the implementation. During these phases of development, the focus of the developer must be upon the outside view of these key abstractions and mechanisms. This view represents the logical framework of the system and therefore encompasses the class structure and object structure of the system. In the later stages of the design and then moving into implementation, the task of the developer changes. The focus is on the inside view of these abstractions and mechanisms involving the physical representations. We may express these design decisions as a part of the statement system module architecture and process architecture. Tomorrow we will discuss about the importance of proper classification. A classification means classification and object oriented development.